Hello, dear colleagues. I welcome you to the first plenary session of the very extraordinary in 2020 conference. My name is Christian Weber from Technische Universität Ilmenau in Germany. We are now looking forward to the first of three keynote speeches. All of them are at 2:15 p.m. Central European Time during Tuesday, Wednesday, and Thursday. Welcome to all our participants. Please mute your microphones in order to avoid feedback loops. I will do so after the talk starts. We are looking forward to a presentation of Professor Mary Lou Maher of the University of North Carolina in Charlotte, United States of America. She is the chair of software and information systems at that university, and also the director of the Center for Education Innovation in the College of Computing and Informatics of UNC in Charlotte. She was a member of the Senior Executive Service at the National Science Foundation, and her current research interests include artificial intelligence and cognitive models of curiosity and creative design. I'm very much looking forward to this presentation. From the abstract, I learned the term of co-creative design systems, which can, based on artificial intelligence, enhance creativity of designers. For questions, which I hope will be there after the presentations, please use the chat function. You can see the button on the top right of your screen and enter at the bottom. You can enter your questions, and I will try after the presentation to sort them a little bit to ask Mary Lou Maher to answer these questions. So that was my pre-presentation talk. I ask Mary Lou Maher to start with her presentation, and this will be live, not pre-recorded. So enjoy and discuss and enter this session. Okay, maybe I can give over to Professor Mary Lou Maher.
Okay, thank you very much for that introduction, and thank you for inviting me. I'm very honored and excited to talk about this research and to hear your views. I'll be talking, I think, for about 20 to 25 minutes, which leaves plenty of time for questions and discussion. So what I'd like to talk about are AI models, and the AI models have transitioned over the years, knowledge representation into deep learning. So I'll be talking about that transition and also the effect of that transition on creative design, computational creative design, and how that's also transitioning into something that's called co-creative design. So as an outline for this talk, I'll start with just establishing some foundations for computational creativity and actually computational co-creativity. And I'll talk about the foundations in AI, and I'll talk about foundations in psychology. Then I'll talk about three projects I've been involved in on AI-inspired co-creativity and how they work, what sort of AI they use. And then towards the end, I'll talk about research directions, and there really are two research directions I'll identify, so you can watch for that as I'm going through both the foundations and the projects. And that is research on AI ability to be creative. And the other is research directions on AI human interaction. because both of those have to be there in order for us to move towards something that we're calling co-creativity. And I want to finish on something that's, I think, so important in this area of research. And we often just do it afterward. And that is, how do we evaluate this research? Because often the way we evaluate the research is what identifies the contribution. And so it isn't something that should be decided at the end. So let's step back and look at this creative design research trajectory. So I've been involved in research related to creative design since the 80s. And it's been a long trajectory that starts here on the left with this idea of knowledge-based design or knowledge-based creative design, where the real challenge was for the researchers was to build knowledge representations that could result in creative design, as opposed to knowledge representations that supported routine design or design that reflected the past. And over on the right, which is still a paper, not a book, is how we can use deep learning to create AI partners for humans. So we're no longer thinking of the AI as being a way to simulate creativity, but rather to stimulate creativity. And in the middle, you can see there's been research in machine learning. In particular, this book on motivated reinforcement learning showed how machine learning could actually identify goals that would lead to creative design. And then this other book on designing for gesture and tangible interaction, the way we interact with computers is changing as well. We're moving away from largely direct manipulation and keyboard interaction into more embodied interaction. So my subtitles here now are important. We're moving from creative AI, where the AI was creative, to creativity support tools, where we think about how we can support human creativity, to intelligent user interfaces. And these are user interfaces that are not supporting us, but they are partners. So the second subtitle, or the third title, is we're moving from simulating creativity in our research in AI to stimulating creativity, where the AI is there to stimulate and augment human creativity. So AI models have been primarily based on cognitive models of creativity. The book by Bowden identifies different cognitive models of creativity. I call out 3 of them here because you'll see them again later in some of our projects. But combinatorial creativity, where 2 ideas come together to create something new. Exploratory creativity, and that's where the cognitive model or the AI model explores a design space and gets to parts of the space that are less traveled, and that's creative. And transformational creativity, and that's where you actually transform the design space by extending it to include things it did not have in the past. And then on the right-hand side, you see Giro and Meyer's work on analogy, emergence, coevolution, and these are cognitive models that became for knowledge-based creative design. Now, the issue with those models and that research was there was enormous effort needed to take what we knew about cognition and transfer it into an AI. And that was that knowledge engineering and knowledge representation task. Another development, which forms the foundation of what I'll be talking about with co-creativity, is this development in deep learning. And so deep learning takes input in the form of input nodes and produces output that's been around since the 80s. But recently with the deep learning, we've realized that what happens in the middle, those nodes that we call layers, provide a latent space. And that latent space has shown to be consistent when you apply operators on the latent space on things like similarity or difference it's relevant and replicating similarity and difference in the representation space of the input. What that means is we can build a knowledge representation, so to speak, that's not human understandable, but machine readable. So that latent space is a vector of numbers. And when we operate on those vectors of numbers, we see things happen in the input and output space that makes sense to humans. So keep that in mind. These deep learning models give us a re-representation that I claim enables creativity without the knowledge engineering. One more foundational concept here. Before I was talking about creative design in the mind of the human or the designer. And then I was talking about creative design through that latent representation that's embedded in the computational model. But there's another important component, and that is what happens outside the designer. So I have my mental model of the design space and my way of transferring and transforming that model, but it's affected by what happens outside me. And this is where stimulation and curiosity become relevant and something to not only be acknowledged, but to be modeled. And the one curve says basically that stimulation on the left-hand side might be boring, and stimulation on the right-hand side might cause too much anxiety, and that there is this comfort zone, there is this sweet spot of stimulation that will encourage curiosity. And when we talk about co-creativity, we want to develop AI that stimulates curiosity, and finding that sweet spot is where we are thinking of developing our systems and our AI models of novelty. So now I want to start talking about co-creativity, and I want to particularly acknowledge that we're transitioning from computational tools for design to computational partners. That means that instead of thinking of the computer as a tool, we're beginning to think about the computer as a partner. And that's through integrating the AI and the interaction models in a way that our interaction or our use of the tool is in some ways similar to interacting with another human with the tool or the computer as the mediator. And what we've done is we've looked at AI inspiration that's based on computational models of novelty and surprise. I'll talk more about that. And that in the work that I'll be talking about today, the AI models are deep learning models of very large data sets of products in the design space. Okay, so the first one, the creative sketching partner. This is one of our early projects where we set up an interactive system where on the left-hand side, you have a canvas for sketching your design ideas that the human sketches into, and a canvas on the right-hand side where the AI produces inspiration. And there's an Inspire Me button and a Start Again button. There's the ability to see or even control how much visual similarity there is and how much conceptual similarity there is between what the designer is doing and what the AI is doing. And that kind of interaction is based on this conjecture, and I'll express them as hypotheses later, that the amount of novelty, that is the distance between the designer's sketch as a design and the sketches of designs in the database, measured through that latent space representation. If it's more novel, we move away from the combinatorial and into transformational creativity. Remembering that combinatorial is the combination of ideas, and transformational is when the design space is transformed. In order to do this, we put categories on our novelty rather than having it be a continuous rank, we categorize it as low novelty, intermediate novelty, and high novelty. So our AI model is actually developed to support and to simulate and stimulate conceptual shifts. So we constructed a visual and semantic model of the sketches. We used a quick draw data set, which has 30 million sketches in it, very large data set. And the visual similarity is based on a deep learning model that was trained on image stroke data, which is representing point 1 to point 2, a line was drawn, point 2 to point 3, the pen was picked up. And so it's a sequence of strokes that forms the data. We found this actually had better accuracy in our deep learning training than a JPEG image. And then the semantic similarity is based on the image label, and we trained up a word-to-vec, or we used an existing word-to-vec model to be able to extract a feature vector for each label on the images. I'm going to give you a little more detail on this so that you can understand what the significance is here. So it takes the user's sketch. So novelty is measured with respect to the current state of the user's sketch. And it extracts the visual features from the model, the deep learning model trained on the quick draw image data. And it locates the user's sketch in clusters, existing clusters. And then those become the conceptual shift candidates with which we extract the word-to-vec features on the labels. And then we calculate the semantic similarity and put a target sketch either in low, intermediate, or high similarity based on visual and semantic similarity. Here's another representation of that same thing, but highlighting that on the top, you see on the left-hand side of the top part of the image, you see the sketch itself. And somewhere in the middle, you see these feature vectors. So the sketch input is the drawing itself. The representation that's used to calculate novelty is a feature vector of numbers. And that's that latent space representation. And you can see it at the top, the feature vector of the images, and you can see at the bottom, the feature vector of the labels or the categories of the sketch, whether it's a chair or a table, is also transformed into this latent space representation, which is a vector of numbers. Once it's a vector of numbers, we can do all sorts of calculations before we convert back to, you see on the lower right-hand side, the sketch and its label. So a table and what the table looked like, a roller coaster and what the roller coaster looked like. So here are some hypotheses. Increasing novelty leads to surprise and curiosity, and that when there's a high similarity between the user sketch and the system sketch, we'll see combinatorial creativity. And then on to the transformational. We did a user study. We gave the users different tasks for different levels of similarity from the AI model. We measured visual similarity, conceptual similarity, and our similarity metric was a cosine similarity between the two feature vectors from the deep learning model. So the cosine similarity is a mathematical operation rather than a human perceptual measure of how similar two images are. I'm going to show you some of the findings. So in the sketches at the bottom, you see 3 sketches in each box. The top left sketch, which is labeled the source, is what the user sketched. The target sketch is what the AI came back with as inspiration. And the new sketch is what did the user do with that sketch. And these are examples of low novelty. So it was similar visually, similar conceptually. And the user typically said, oh, I can just combine that with my sketch. And they would put a fence on the bridge, or they would use a fence-like structure to construct the base of the bridge or the support for the bridge. Intermediate novelty, here we saw, and this is based not just on what you're seeing, but on a retrospective protocol where we included what did the user say. And they said things like, oh, this makes me think of scaling up the shade on the street light or changing the scale or the size of the base. And so they began to think about the design space in terms of the variables and how this sketch inspired them to change their variables. And then high novelty, this is where we saw when the inspiration was conceptually and visually distant, that a speedboat made the person think about the chair having more organic shape. And so it transformed it from a standard chair into a much more unusual chair, and integrating sort of the ideas or the concepts that they identified in the sketch rather than the geometry of what they saw in the sketch. From that, we transitioned into the collaborative ideation partner where we controlled the amount of similarity. And the idea here was not to study the product, but to study ideation. And so the contribution here is really in the evaluation. How do you evaluate or measure ideation? And we adopted the research from Shah and others to see what does it mean to calculate novelty, variety, quantity, and quality of ideas in a co-creative sketching task. And the novelty was how many times did we see ideas in the design task that other designers didn't have. So these were novel across the sessions, where variety was how many ideas were actually generated within the session that were new, and the quantity was all ideas. And then the quality was based on Emma Beale's consensual assessment technique, where the judges judged it. In all of our cases, except one, we saw an increase in the novelty, variety, and quantity of ideas when the condition was AI inspired compared to when the condition was random inspiration. We also looked at the process and found that when the participant was experiencing the random inspiration, typically they didn't find any inspiration from the sketch, where when we varied the visually and conceptually different sketches, they talked about how they would incorporate that into their design. And we saw this co-evolutionary process where the design was actually influenced by the AI much more than it was in the random case. We were sort of debunking the idea that no matter what you give someone, it will be better than having no inspiration, and that serendipity research sometimes is associated with random ideas can be as inspiring as ideas that are relevant. And in our study, we're showing that that wasn't what we observed. And now finally, on the third one, I wanted to talk about Arnie. So in the previous examples, we had the AI was doing the functional sense making, which is the image at the top, where the communication between the AI and the design was based on observing and responding to the sketch or the product itself, and not based on some of the techniques that we as humans use, which is the communication directly between two people, or in this case, the communication between a person and the AI. And what we integrated into our AI decision about what to inspire the person with was emotion detection. And so we came up with a set of rules for whether the AI should converge, which is give something that is similar to what the designer is doing, or diverge, give something that is novel in the design space and very different from what the user is doing. And with those rules, we did a user study, a very exploratory study. You see the task was more of a configuration task than a sketching task, where they added objects to design a room which was an office space. With emotion detection, we found that the designs were fairly coherent. The AI contributions were considered relevant and interesting. And without emotion detection, we see that what happened was the user would take the AI's contribution, or the random, they thought it was all AI, the random contribution, and move it over to the side and ignore it. And only their ideas were left in the design. Okay, research directions. I want to leave time for questions, so I'm going to try and wrap up now. The AI models of novelty and surprise. This is an important area of research. How do our deep learning models work? They need very large data sets. Where do those come from? And do we need to have in those data sets anything more than just the visual representation or the words? Do we need the engineering in there, or will it construct a latent representation that captures the engineering? And that is, can we go beyond visual and semantic novelty and into engineering principles? So I think we need more approaches to representation and to latent space generation. We also are thinking of moving our computational metrics from novelty, which is about difference, to more explicit representation of surprise, which is about expectation and therefore is probabilistic rather than distance. And then the second major research direction is this interaction between the human and the AI. Most of the models we see are what we're calling intentional models. And that's where the interaction is through direct manipulation, embodiment, conversation. I intend to communicate this with you, versus consequential models, which is emotion detection, body movement, biometrics, where I'm not communicating intentionally, I'm communicating with, I'm just reacting, and the AI can detect my reactions. Finally, I promised I would come to evaluating. Evaluating is an interesting problem in human AI creativity, because who's evaluating? Is the AI evaluating what the human is doing and saying, hey, that was very creative? Or is the human evaluating their own creativity? Or do we have an expert who's looking on? Is the evaluation occurring during the process? So the AI could say during the process, that's a great idea, go with that one. Or are we evaluating it at the end? And the what are we evaluating? Are we evaluating the product, which is that image up on the top left? Are we evaluating the cognitive processes inside the human's head? Or are we evaluating the interaction? And then how, there's so many methods. Is it a protocol study? Is it a checklist? Are there metrics? Are we doing it in the lab? Are we doing it in the wild? So I'm going to conclude here and just put some ideas up here. So deep learning models produce a representation space for measuring novelty and surprise that have none of the overhead of knowledge-based design. The AI-based co-creativity transforms the AI from a tool to a partner, and the partner is modulated by novelty and surprise. And that measure, that inspiration, actually can have an impact on our creativity ideation and can have an impact on emotion. And the research directions, then, the AI abilities to respond. How do we increase the ability of the AI? How do we study the interaction? And how do we evaluate the co-creativity? I want to acknowledge my collaborators. These are the faculty and the students who have worked with me on the project, and I want to acknowledge the National Science Foundation. And with that, we'll open it up for questions, and I'll stop sharing so I can see.
Thank you very much, Lou Maher. Can you hear me? Yeah. Okay.
Yes, I can hear you. Thank you.
I haven't seen questions in the chat so far, so maybe you can post your questions to the presenter. Before we go into that, maybe I can say that in one of the next sessions, that is number 221, we have artificial intelligence in design with some more shorter presentations on this area. Maybe I can start with a question of myself. You have this semantic category. I don't know exactly what this is based on, because I don't know what is the word to vec features you mentioned in your presentation.
So the semantic, if you've used an email client, that when you're typing in your words, it might finish your sentence. And so how does it do that? Well, the way it does it is it takes the words that you are typing and it puts them into one of those word-to-vec models, and it predicts what might come next. And so word-to-vec is a deep learning model that's been trained on, let's say it's trained on all the emails that anyone's ever written using Google Mail, or it might be trained on Wikipedia. So ours was trained on Wikipedia, and the words that we have to describe the design task. So design a bridge to go over a stream in a national park. And then we have the words that describe the sketches in the database. And we transform those words into these vectors. And then we say, how similar is the word bridge to table? And that's the semantic similarity, by doing that cosine similarity of those vectors. So the semantics, what this means is we don't need to build these huge knowledge engineering databases. We can just use the words that describe the design and measure the distance between the words and let the deep learning model construct that knowledge layer. We don't understand it. It's a vector of numbers, but it seems to preserve distance in the space of the knowledge representation when we do the measurement in the space of the numerical vector.
Thank you. I see a couple of questions in the chat forum. Maybe start with Claudia Eckert's question. I don't know whether you can see them as well on your screen. Human designers use inspiration differently depending on whether they are working on details or on overall designs. And do you mirror that in your research, or will it be one of the next stages?
Yeah, thanks, Claudia. So what we found is that the inspiration, if you're working on details, is better if the similarity is very high, because you want something that's close to what you have, even if it's not the same. But if you're working on the conceptual or the overall design, where you're in the ideation phase conceptually, that you want inspiration that is farther away. It encourages you to think beyond your current trajectory. And so you're right, we use inspiration differently. And in one of our systems, we actually let the user control how much visual similarity and how much semantic similarity for the inspiration, rather than letting the AI control that. In the emotion-driven system, the AI didn't wait for the user to say what they wanted. It based it on whether they were having a high engagement or low engagement with the design task, or whether they had high positive emotional response or high negative emotional response. So it wasn't just the stage of the design, but the emotional response of the user.
I see.
Claudia also mentioned pedigree. Doesn't it matter what the pedigree is? Because it does matter to human designers. Who designed that? And that's true. It does matter what the pedigree is. And so we haven't tried to think about how deep learning models might capture pedigree in terms of famous, not famous, in terms of this firm or that firm. But I don't see why we can't. We just haven't even gone to that part of the representation.
I see a question addressing the involvement of non-technical people, and also addressing well, the lack of transparency in artificial intelligence. Maybe I can link it to a question of myself, because we have been working with autoencoders in completely different circumstances. But the problem I always have with these is you don't have any control about the parameters and the relevant features that the autoencoders detect. And that is disturbing to a traditional engineer, maybe.
So the question about the non-technical people with AI support, the intention here is to support designers, not non-technical. I mean, we wouldn't trust the design of a bridge to someone who doesn't know anything about bridges. So the intention isn't here to take people who aren't engineers, give them AI support, and all of a sudden they'll become creative engineers, but rather to augment the creativity of the person who understands what they're doing. And what we've done before when we've tried to support them with knowledge-based systems is they've been highly critical of the AI producing content or contributions to the design that weren't very well informed. And so there was that frustration level. So we're not trying to involve non-technical people in designing technical systems, but rather to support the technical people. So how do we address the lack of transparency in AI is the next question. Is what if the person wants to know, why did you think that was relevant? And what we're doing with the inspiration is letting the relevance be constructed by the designer. So it's not about the AI saying why it's relevant. It's measuring distance, it's measuring novelty, and it's measuring surprise. And the person then constructs the relationship, makes the analogy work, rather than saying that that analogy emerged through the AI reasoning. Because the AI representation is not the same as the human. The idea is to complement this latent space representation with human understanding of the engineering. Back to the layers and the parameters for deep learning, we use a simple model for determining whether it's a good latent representation. So we use autoencoders. When it can take an input layer and be trained to produce an output layer through the encoding and decoding process, when that achieves a level of accuracy, in other words, they are the same, then that latent space becomes a representation that mirrors the difference in the representation of the input and output layer. So that vector of numbers, which means nothing to us, if two vectors are close to each other in that latent space, then they're similar to each other in the input space. And so it's not a matter of how do you get a good model that is relevant to what we're thinking. It's how accurate is the autoencoded model so that we may preserve that relationship in the latent space to the input space.
I see a question of Daniela Pigosso backed by several other people. Maybe I can reformulate it in a more general way. If you put in basic ideas, do you get out more than what you put in terms of other behavior parameters, which you might have overlooked in the first place? This is formulated, can you predict systemic behavior across the product life cycle?
So I think yes. Have I done it? No. But let me tell you why I think you can. We look at GP2 and GP3, GPT-2, and what that's done is it's done it for language. When people are typing in words, it can predict what'll come next. And in some cases, it predicts something that you like even better than you would have thought of. And that's in all of us experience this to a certain extent when we type an email and it finishes our sentence. The other example is that engineers have built deep learning models of mechanical systems, engines in airplanes that replace or build the physics model. So you have a physics model that you can run, and it might take 24 hours to get the answers, but you train the deep learning model on the input and the output, which is the physics. And then it generates that latent representation that gives you the physics without doing what we would call physics. It just runs it through the model. It could predict the physics from the geometry because it trained the deep learning. And we didn't need to encode the physical principles. So that leads me to believe that, Daniela, if we have an input node that says, what are the behaviors of these systems, these products? If that's our input into a deep learning model and you put in a new system, it should be able to predict the behavior if you have enough data to train the model. So I haven't done it, but I see there are similar things being done in language and in physics.
This is interesting because it mirrors the question back to the parameters you put in. If you don't.
Right, that's right. That's right. Without having to do all that knowledge engineering, which is not only difficult, but error prone.
I also see a couple of questions. Maybe you could explain it to the audience. If you put in past data, how do you expect novelty?
That's really good. I was waiting for that one. So what we're doing is putting in data about a design space. And because the representation is a vector of numbers rather than the input data, we can move to parts of that design space with that numerical representation that wasn't in the original data. So you train it up with 30 million sketches, and it can actually get to a space in the vector space that is none of those sketches because it's operating in that latent representation. So the key to producing novel ideas is to build a re-representation, a different representation of the design space, move around that space, and then come back out, decode back into that representation space. That's where novelty happens.
Maybe a question I had, what about the complexity of tasks which can be handled today, which maybe can be handled in the future?
So I think we don't know how far this can go. If you look at what's happening with natural language and the use of deep learning models in natural language, we're seeing very complex natural language generation work very effectively with these deep learning models that know nothing about language. So the deep learning models don't know what a verb is. It doesn't know what a noun is. It just has this latent representation with which it generates things that weren't there before. And they seem to make sense. And so when we talk about complexity, maybe complexity isn't the question because it was complexity when it was knowledge engineering. Learning models, what are the representations we give it, and how do we, this curation problem, how do we find enough design data to construct these deep learning models? And it's a matter of scale, size, rather than complexity. The complexity is subsumed within the deep learning model.
Maybe as a last question, just dropped in, but that's maybe also a problem. How do you collect the large data sets needed for this deep learning algorithms?
I think that's the new knowledge engineering task, and it's called data curation. Hopefully it's not as hard as knowledge engineering was. Data curation means now when we generate our designs, we need to save them in some digital format that will support and enable this deep learning process. It may just be the visual data, the image, the geometry itself. We don't need to put in the physics. We don't need to put in the function. That can emerge as an emergent property. So I think it's a data curation problem. How do we build these data sets rather than how do we construct knowledge from our experiences? I love Panos's question here. What is my assessment as to how this line of research will become mainstream tools? They're already there. So I think it's happening. The question is where do they go from this very early stage into something that's more comprehensive? We're still using these systems as tools. How do they become partners?
In order to keep the time frame of the conference, I have to express many thanks to Mary Lou Maher for an inspiring presentation, and also to our audience for the discussion. I could not place all of the questions to you, but maybe we can discuss in one way or another, even though it's an online conference. We now have a little less than 15 minutes breaks, and please remember to join the sessions, which will start at 3:15 again, and one of those is artificial intelligence in design. Thank you very much. And maybe I can ask our moderator. I don't know what to do now in terms of this hop-in system.